Alright, so welcome back to the fourth and final video. In this video, we'll be going over programming or coding in loss for our neural network from scratch. So we'll be creating a loss class, and then we'll also be using specifically categorical cross entropy. That's a formal loss for this specific neural network, right? And I've already programmed it in. I've already coded it in. So we'll be going over what all of this exactly is in just a second, but um, moving on, we'll also be talking about optimization. And with optimization, though, we won't be coding it in Scratch in this neural network you see right here, right? And there's a reason for that. So one of the prerequisites, or because calculus isn't a prerequisite for these videos, it'll be hard for us to implement optimization in from scratch because you can kind of already tell how when we implement all these functions, all these different parts of a neural network into like code from scratch, right? We kind of have to like uh program in the math like individually. Like we have to somewhat understand the math at least to like actually be able to represent it, right? And because optimization relies heavily on concepts that are based in calculus, like calculating the gradient, so getting the gradient vectors, using partial derivatives, and then concepts of differentiability and like using tangent lines instead of like slope. Like these concepts are kind of exclusive to calculus, so we won't be going into programming from scratch because you'll actually have to kind of have a solid understanding of what calculus to be able to implement it from scratch. So instead, what we'll be doing is moving forward to a framework. So we'll be using a Python framework, TensorFlow, right? It's a machine learning framework, and we'll be using Keras specifically. And we'll be using that framework to create a neural network, and then it'll have backpropagation and optimization already implemented into it, so we can kind of see how that works. It'll have the training parts of the neural networks implemented into it. It'll have the testing part of the neural network implemented into it. So we'll be going over the code for that as well. So it'll be kind of like a summative, like completion part of like the entire video course. We'll be going over everything we kind of learned and what we can kind of understand from like a neural network that's been programmed in a framework rather than from scratch. So because we've learned kind of all the fundamentals and like the basics for a forward pass, we should be able to kind of understand and pick up what's going on in like the framework code pretty easily. So it'll be like kind of a review as well as an introduction into optimization, but it won't be a very deep dive into optimization. So now that we have that out of the way, why don't we go ahead and start talking about the loss that we coded in, right? All right, so with the introduction out of the way, why don't we actually start talking about how to calculate categorical cross entropy, right? So in our code, let's go back to our code real quick. We have categorical cross entropy created as a class, and we have all this math written out, and we've programmed it, or I've already programmed it into existence, right? But before we actually interpret this, why don't we actually mathematically figure out how to calculate the categorical cross entropy or loss, right? And um, actually, before we even do that, why don't we talk about why loss is important for a neural network, right? And we've discussed this concept before, but the whole point of a neural network is to improve itself based on off of how wrong it was, uh, as how wrong its prediction was to compared to the actual result, right? And we can quantify the how like the wrongness, right? It's not a real word, but we can quantify that wrongness as loss. And this loss metric, right, is very useful for the computer because it wants to minimize it as much as possible. That's the whole point of the neural network. It wants to minimize this loss um, as much as possible, and it uses calculus to do that. So that's why loss is important, right? Because without loss, you won't be able. How would you be able to quantify the wrongness of this neural network? How would it be able to improve itself without knowing how wrong it was, right? So that's why it's important to get loss. And with that out of the way, why don't we actually talk about figuring out how to get this specific type of loss, this categorical cross entropy. All right, so this big clunky equation you see up here is how you pretty much calculate the categorical cross entropy. So this is what we're calculating for. It's the categorical cross entropy. So it's like the loss. And this can be simplified down, right? So we don't want to, let's not interpret it as this big clunky equation. Let's simplify it down first and then interpret what it is, what it's asking us. So we can rewrite this as negative log. Oh, y, I, k, okay, in which y is equal to the predicted values. Let me actually kind of improve my handwriting. Predicted values, and k is equal to the target label index. All right, so we'll talk about exactly what k is, but we should be pretty familiar with this is. This is pretty much going to be our output for the softmax function, right? So that's the final activation function. We know that the softmax is what we're going to be applying to like the output of the entire neural network, right? To get a probability. That is what we're going to be treating as y, right? And I just means like the number, like the sample number in the set. So like the first sample, second sample, third sample. So it just means the I just means to iterate throughout the entire set of outputs. And so that's pretty much how you interpret this equation right here, right? So you're basically taking a negative log of the predicted values times the predicted values of the ith index times the target label index. And yeah, so let's why don't we start discussing what the target label index is, right? And we get the target label index from one-hot encoded vectors. And what are not hot encoded vectors? All right, so what are one-hot encoded vectors, right? So pretty much one-hot encoded vectors are one-dimensional vectors that are n classes long. And what are classes really, right? So classes are the classifications that your data could fall under. So when using categorical across entropy, you usually use data that has been classified into different sets, right? So it has meaning. So for example, you could have a data set of images, right? And those images could be classified as either a dog, a cat, or a human, right? So in this case, we have 1, 2, 3 classes. So our one hot encoded vector will be three indexes long because it has three things. The data can be three things. It could either be a dog, a cat, or a human. And the one hot encoded vector, right, is initialized to zeros. So initially it would be like this. But since the one hot encoded vector changes depending on what data you give the neural network, right? So say you gave the neural network an image, right? The one hot encoded vector will represent the label of that image. So represent what it actually is, so that at the end the computer can predict whatever outcome it got to whatever the true value of that image was in order to get the loss. So how does it represent which image is correct and which image isn't, right? So these indexes in this one hot encoded vector, right? They're dependent on classes. So we have 3 different indexes in this one hot encoded vector. And because they're dependent on classes, each one of them represents a class. So this index could represent dog. This index could represent cat. This index could represent human, right? And the one hot encoded vector is initialized all to zeros, except for the one index that is correct for the data. So say you pass the data that was for a dog. So you pass an image of a dog to a neural network. The one hot encoded vector for that neural network will look like, for that data, for that specific data that you pass in that neural network, will look like this. It'll look like a 1, 0, 0. So if the label, right? So if the label was 0, this is what it will look like. And label 0 just means the 0th index of the classes. So this would be the 0th index, this would be the second index, this would be the first index, this would be the second index, sorry. So label 0 just means that in the 0th index of this one hot vector, there's going to be a 1. Because that index represents a dog, and the data we sent into the neural network is an image of a dog. So say we sent an image of a cat, so the label would be a 1. The one hot vector would then turn into 0, 1, 0. If we pass an image of a human, so if it was 2, it'd be 0, 0, 1. So there's only going to be one index that's a 1, and everything else is going to be a 0 in the one hot encoded vector. And the number is a 1, right? Because that 1 represents 100% chance. So 1 represents 100%. And what do I mean by 100%? It just means that the data has a 100% chance of being a human in this case, because the computer already knows what the image is supposed to be. So the true value of this data is 100% human, right? And this is different from what the computer would output. After maybe if we say we sent this data for a human through the network, and this is what the one hot encoded vector would look like. The predicted outputs might look something like this. It might look something like 0.12, maybe 0.8, right? And then maybe a 0.80, right? And all these sum together add up to 100%, right? But the computer isn't 100% confident that it's a human. Maybe it's only 80% confident. So this 80, this 0.80, it represents that the computer is 80% confident that data that you pass is a human, because it's in the second index, right? And it's going to compare that 0.80 to this 1 up here, to this 1. And then it's going to calculate loss based off of that. So that's what our K value is, right? Target label index, this is what it is. This one hot encoded vector that has a target that has the label, right, to be set to 1. So it has a target label, and that label is dependent on the index. So quickly going over exactly what I just said, the target label, so what the data is actually supposed to be, is determined on the index, is determined by the index of this one hot encoded vector, right? So the 0th index is going to be whether or not it's a dog. The first index is going to be whether or not it's a cat. The second, oh, I misspoke. Sorry. The 0th index is going to be for dog. The first index is going to be for the cat, and the second index is going to be for humans, right? So that's pretty much what it means. It's asking this is pretty much asking what the true value is. This is asking what the predicted value is, to simplify everything down. All right. So say we were to implement this equation back into the using some of these values down here, right? So let's say we used this one hot encoded vector right here, this 0, 0, 1, and then these values down here to get our results. What our plugging and chugging would get us this. So we get, actually it's Li, so why don't we represent as Li? So Li is equal to, it's going to be the sum, right? It's always a sum, but I'll show you why it simplifies down to this in a second. But for now, let's stick to the sum. So it's going to be the sum of, let's see. So it's going to be index 1 of the one hot encoded vector. So it's a 0. That 0 is going to be multiplied by 0.12. So it's going to be the sum of the negative log of 0 times 0.12 plus the negative log of 0, the first index, times the first index of the actual results, right? So 0 times 0.8 plus the final one's going to be a 1 times 0.80. The minus log of 1 times 0.80. Let me scroll over actually. All right. So you guys can kind of already see how these two are going to cancel out, right? It's the 0 times a number is just going to be 0. The log of 0 cancels out. So that's why this equation just becomes this, right? It just becomes the negative log of the the predicted values times the specific target label index, right? Because the true equation, right, is the summation of all the one hot vectors times the predicted outputs, right? So that's what we just did. We just did the summation of it, right? But in reality, since the one hot vector is initialized with zeros except for one value, everything but that specific target index is gonna just disappear, right? Because they're just going to be a 0 multiplied into whatever probability that the computer spit out. So they're all just going to disappear. So all the computer is going to care about is pretty much whatever index the 1 is in. That's the only index that the computer cares about. So in this case, it would be the second index that the computer cares about. So these two values in the 0th and the first index of this predicted outputs array, they're just gonna get cut off, and it's gonna only care about this 0.8. So this equation now looks like this. It looks like the negative log of 1 times 0.8. So it's just gonna be 0.8. I'll write it as 0.8. 80. And then this is going to be, actually, let's go ahead and calculate this, I guess. Alright, so the negative log of 0.8, it'll be 0.0969. 0.0969 is going to be the loss of this neural network. So 0.0969. And that should make sense, right? Because it's an 80% result compared to a 100% result. So if we change this number, right? So say we change 0.8, so from an 80% accuracy to down like to, let's say, a 55% accuracy. Right? Why don't we compare those results? Or I want to compare those results. So let's see, negative log of 0.55. And the loss increases, right? The loss gets much, much greater. So the loss now becomes 0.259. So that's kind of how categorical cross entropy loss is calculated. It uses this like one hot encoded vector that basically tells the computer which what the data is classified as, and then it compares that classification to whatever the computer thought, whatever the computer's confidence interval, whatever the computer's confidence scores were for each of the classes, right? So going over what they were, the computer thought there was a 12% chance of the image being a dog, an 8% chance of the image being a cat, and the 80% chance of the image being a human. And then it compared that to the 100% chance of the image actually being a human, and got the loss of 0.0969. And after calculating this loss, right, the computer's going to use optimization to try to get this loss to be smaller and smaller by adjusting the weights and biases using some calculus. So that's pretty much what, or that's pretty much how you get categorical cross entropy loss. So I think we should be able to start taking a look at how to actually program it from scratch. All right, so a quick fix I need to make. So a quick fixing I need to make regarding the math I did last video, or like the last clip. Sorry, so it should still be in the same video. This negative log right here, right? These negative logs that I'm summing. This the one hot encoded vector value right here, this 0, and this 1, they don't belong inside of the log. They are actually outside of the log, so it would look like this. This is what it actually looked like. It would be the sum of negative of 0 times the negative log of 0.12 plus 0 times the negative log of 0.8 plus 1 times the negative log, kind of writing upwards, times the negative log of 0.8. So this is what it would look like. It would be the one encoded vectors on the outside and just the log of the predicted values. So that's just a quick fix I had to make regarding some of the math I did earlier. This doesn't change too much except for the fact that the log of 0 I do not think actually equals 0. So what I said earlier kind of doesn't make sense. So if we go ahead and ignore the YouTube, but if we go ahead and plug in actually the log of 0, yeah, it's we can't do it. So my mistake on that. I quick fix real quick, and everything should still stay the same because conceptually we want to get rid of these two zeros. So it should still be the negative log of just 0.8. So yeah. All right. So how would we calculate for this loss if we were given not just like uh, one batch of outputs, we were given a multiple batches of outputs. So say our outputs were like something like, let's say a 0.7, 0.2, and a 0.1. There were a 0.6, 0.3, and a 0.1. And then there were also a 0.5. Actually, no, let's do 0.55, point, uh, 0.40, and a 0.5. Let me start making these numbers look a little bit better. 40 and a 5. Okay. So what if this was our outputs for the softmax function, right? So this would be the first set of inputs sent in. This would be the second set of inputs sent in. This would be the third set of inputs sent in, right? So what if you had 3 batches of data that we sent through the network and we got this as an output? What would our one hot encoded vector look like, right? So we already know that we have to represent this one hot encoded vector as a 2D array because we're representing multiple inputs. So we know that we're gonna have multiple one hot encoded vectors to represent. So start off with a 2D array, and let's say for the first one, we were we were trying to predict whether or not the same situation, cat, dog, or human, right? So for the first one, the one hot encoded vector could probably be b, let's say a 1, and a 0 and a 0, right? Because what did we say the first index was for a cat? It was a dog, So in this situation, since it's in the 0th index, uh, since the computer knows that the image is a dog, it'll put a 1 in the 0th index for the first one hot encoded vector. Maybe for the second input, right? The image wasn't a dog. It was maybe a cat, right? So maybe the image was a cat. So the one hot encoded vector would look like this, a 1 in the middle, right, where the cat index is. And yeah, that's where the cat index is. So that maybe that's the second one hot encoded vector. And that corresponds to this set of inputs right here. For the third one hot encoded vector, let's say that the computer sent an image and the image was actually a cat instead, right? It's a image of a cat as well. So it would do a 1, a 0, a 1, and then a 0 as well. So this is what our final one hot encoded vector would look like. And we made this one hot encoded vector kind of with no like backing. Like we kind of did it with no regards to the actual data because we were just making up whether or not our imaginary data set or imaginary data points like 0.7, 0.2, and 0.1. So we're kind of making up what our imaginary batch inputs are equal to and just kind of making a one hot encoded vector based off that. All right, so how would the math really look for this, right? So how would we get the correct losses for these 3 inputs, right? And to start off with, we know we're gonna get 3 losses, right? One for each individual input. So we know our results are gonna have to be in an array, and it's gonna have 3 different values because we have 3 different losses because we have 3 different inputs or outputs. Sorry. Um. So how do we calculate it, right? We basically take we use these 2 arrays to determine what our confidence intervals that we want are, and then we just apply a negative log to them. Right? So what do I mean by that? So look at remember the equation we used up here, the negative log of just the one hot encoded vector times the one hot encoded vector times the negative log of the predicted outputs, and how like all the other predicted outputs don't matter other than the one that's in the label that in the index of the label that the data actually belongs to, right? So what we can do, right, is take a look at these one hot encoded vectors and then take a look at these outputs individually and then index them and pull the confidence the correct confidences or the confidence values that we need to calculate the loss, right? So it might make more sense when I start doing it, but for stay with me for now. So let's start with the first set of outputs, right? So we have 0.7, 0.2, and 0.1. There's 3 elements in this array, and it indexes up to 2. So it's 0, 1, and 2. This belongs to that set of outputs. So if we take a look at it, there's a 1 in the first in the 0th index, right? Which for our purposes means that it's a dog. So for this image, the computer is told that the image is supposed to be a dog. So it takes a look at the same index value in the outputs array. So since it's in the 0th index, since the 1 is in the 0th index for this one hot encoded vector, it'll take a look at the 0th index for this vector and pull a 0.7. So the first value is going to be a 0.7. Oh, it's going to be a 0.7. It's going to do this. The second one hot encoded vector is going to do the same thing, but for the second set of outputs. So since there's a 1 in the first index, so in the first index, which indicates that it's a cat for our purposes, it's going to pull this 0.3 because it's in the first index of the outputs. So that value is going to be a 0.3. And for the third set of outputs, there's also a 1 in the first index, which means it's a cat, so it's going to pull this 0.4 from the first index. So it's going to be 0.7, 0.3, and 0.4. And at the end, we're going to apply a negative log to this entire array. 0.4. And if we want, we can go ahead and just do the math, but the outputs is going to look like this. These are going to be our probabilities. It's going to be the negative log of 0.7. I'm just going to leave them unsimplified or expanded. And then this is 0.4. So this is what our final array for our losses would look like. And each of these indexes, so this is index 0, index 1, index 2, they represent the losses for every set of inputs sent in. So if you had like 400 inputs sent in, 400 batches of inputs sent in, you'd have 400 separate losses for each of those batches. So it's kind of how you calculate it for a 2D array, which just indicates multiple batches of inputs sent in. All right, so now that we have that under our belt, I think we can start coding. All right, so one more thing before we continue, right? So remember how we discussed earlier about the log, or we explored the log of 0 and how we got a negative infinity or an infinitely large number or an infinitely small number? That's an issue to us, right? Because say we had an input of 0 in any of these indexes for any of these inputs, our batches of inputs, right? Oh, we gotta do that. So say we had a 0 for any of these numbers, right? And the one hot encoded vector also belonged or also pulled or also was of the same index of that 0, sorry. So we end up with a 0 in our final array. So it looks like maybe this 0.3 and like a 0.4. If we take the log of this 0 right here in the 0th index, it's going to return an infinitely large number, right? And that's not going to work for our neural network, right? It might work because it'll return the computer when it compiles it in the code. It'll return something like this. It'll be like infinite, and then it'll return the negative log of 0.3, and then the negative log. My handwriting is getting worse and worse. Sorry about that. Negative log 0.4. So it might return something like this, right? And this is okay because it's technically like it's still kind of accurate, because if it was 0, if it predicted a 0, it's infinitely like wrong. There's an infinite loss because it's infinitely wrong. So it kind of makes sense in that sort of case, and we might be able to get away with it by just like having this, right? But we can't get away with it when we do the next step in calculating loss, right? We have to take the mean of all these values to calculate the loss for the entire batch. So we're calculating the mean loss, and we're improving off that. Because we can't improve off 3 separate losses. We have to improve over one holistic big loss. So at the end, when we calculate the mean of this, so when we do the mean of this, if we had this infinite number in here, or if we had this infinite value in here, it's gonna destroy this entire function. So it's gonna return definitely an error of some sort, probably like a computational error, because you can't work with infinity. You can't add infinity to these values and divide by however many values there are, because that's how you calculate the mean. So it's gonna return an error. It's gonna return a compiling error. So we can't have that happen. And there's a way for us to get around that, and it's just by clipping or like adding or subtracting. It's a minuscule value, so something like 1 times 10 to the negative 10 or something like that. 10 to the negative 6, let's say. Adding or subtracting this to our inputs so that it'll never equal 0. So that's also something we have to take into account when we're coding it. And I won't show I actually will show that, yeah. It's going to be implemented in the code, so we'll go ahead and take a look at it right now. Alright, so let's take a look at some of the new code we implemented. I also added some labeling for all of our parts of the neural network. So this is the layer gen part, these are the activation functions, and now this is the loss. There are a couple of notes as well. So Y, for our purposes, is the intended target values, and output is just the output for the softmax function. And so first I created a class, a general class for loss that has a derive function in it that takes in itself, it takes in the outputs, so like this whatever whatever the softmax outputs are, and then it takes in the intended target values. In that function, we have sample losses, which is pretty much like the losses per set of inputs that you send in. So that would pretty much be like, where is it right here? So it would be like this. So these would be our sample losses. This would be the sample loss for the first set of inputs that we discussed, like this. This would be the sample loss for the second set of inputs. This would be a sample loss for the third set of inputs. And I can say that these are inputs, right? Because they were once inputs. It takes 3 inputs in a neural network to create 3 outputs, right? So you can refer to these as like, I mean, I guess it would be better to refer to them as outputs. Yeah, okay. So three outputs. So these sample losses are respective to these 3 outputs. Oh man, go back. Okay. So that is what it that is what it pretty much calculates. It solves for the sample losses, so it gets a vector, it gets an array of the sample losses, and that's dependent on however many batch set size of inputs that you send in. So if you send in like 30 batches of inputs, you get 30 sample losses. The data loss is pretty much the mean of all the sample losses. So since we need one number to represent the loss, we just take the mean of all the losses, and then we return the data loss. So that's what this function does. The function derive pretty much calculates the loss. This is like a little function that calculates loss. And this class is general. It applies to all types of losses, not just categorical cross entropy loss. So now specifically programming and creating the categorical cross entropy that we just discussed and try to and figure out how to solve. We create a class that represents it, and we pass it the loss class as well. So we encode the loss class as well. Our samples are just dependent on how many Y predictions we have, right? So if our computer predicts 5 different outcomes, that means there could be 5 different classes or classifications for this neural network, right? So for this data set, sorry. So samples is basically like the classes, how many of them there are. Ypred_clipped is, remember how we discussed how we can't have the log of 0? This is pretty much what ensures that we never get a log of 0. It clips all of the Y predictions, so which are these Y predictions, right? They are the outputs of the softmax. It clips all the outputs so that they end up between 1 to the negative 7 and in between 1 minus 1 to the negative 7. So it creates like this range that ensures that it'll never equal 0. All right, so for the next two lines of code, this if and elif statement, they're pretty much just to catch two different types of classification. So we discussed how you can classify the data in a neural network by using one-hot encoded vectors, right? There's also another way for you to do it. It's called I don't. It's instead of using a 2D vector for multiple batches of inputs, you still only use a 1D vector. So what would that look like, right? So let's say your classes that equal dog, cat, and human again, in which dog is 0, cat is 1, and human is 2. So you have 3 classes. Um, this vector, this 1D vector rather than a one-hot vector, it would look like this. So say for the first set of inputs that you sent in, it was a dog. So the first value is going to be a 0. The second set of inputs you sent in, their true value was a dog as well, so it also put a 0. The third set of inputs you sent in, the true value was a human, so it'd have a 2 right here. The fourth set of inputs that you sent in, maybe it was a cat, so you'll have a 1 right here. So these don't really depend on the index. They kind of classify the inputs based off of the number that is associated with the class. So this specific index doesn't refer to just dogs. This specific index doesn't refer to just cats. This specific index doesn't refer to just humans or something like that. These are all just these are all classifications of a series of inputs. So these indexes represent are the number of batches that you send in. So this would be the first batch, this would be the second batch, this would be the third batch, this would be the fourth batch. And the numbers inside of those indexes are what determine the actual value of those sets of inputs. So this is what a 1D array would look like. If we were to do let's say one hot vector to represent this, it would look like this. It would be a 2D array, but it would be a 1, 0, 0, because the dog is what the first value is supposed to be. Second vector will look the same. Third vector, since it's supposed to be a human, will have a 0, 0, and a 1. And the final one is supposed to be a cat, so we'll have a 0, 1, 0. And then this is going to be the final one hot vector. And this is going to be the 1D vector that someone might use as well to calcify these outputs. And these two are completely different in the way that we get, in the way we determine the correct confidence intervals that we want to pull, right? So this one, we use this equation in which we sum the correct indexes. So we go from the first neuron, we go to the first index, we get 0.1. Go to the second neuron, we go to the second index, 0.3, get a 0.3. Go to the third neuron, we go to the second index, we get a 0.4. So this is what we do for one-hot encoded vectors. All right, so you can kind of already see how these one-hot encoded vectors are completely different from these 1D vectors that represent what class or what an actual input is equal to in the data set, right? So they're kind of different in the way they do things. So in our code, we kind of have to deal with them in two different ways. So this just checks to see if the length of y true, right? If the shape of y true is equal to 1, which means it's a 1D array, it'll run this line of code to calculate the confidences. Because you're using a 1D array, you have to use a different set of code than like than calculating using a one-hot vector. And this checks if the shape of y true is 2, which means it's a 2D array. It'll calculate the confidences in the way that we know of, in which it just multiplies all the one-hot vectors and the indexes for every single input. And it'll do this by row. So yeah, for every single input, because the inputs are ordered by rows. And this can be simplified down to just going to whatever index y true is for every single neuron. and then getting that value for every single neuron in YPRED clipped. For every single, not neuron, sorry, excuse me. For every single batch of inputs in Y clipped, it'll go to whatever index Y true is and pull that confidence. That is pretty much all this is saying. Okay, so it'll return the log likelihoods, and those log likelihoods will then be used later in the derived function in this loss class. So when we create the instance of the object, so we set loss function to equal this class. We can actually call functions in the loss class because we have it kind of embedded in our second class. So we can run loss function dot derive, and then we'll pass it the softmax activation output, and then we'll pass it y, which is pretty much our one hot encoded vectors. So let's say, yeah, those we haven't initialized them to be anything yet, but those are our one hot encoded vectors, and we'll pass it those two things, and when it runs derive, where is derive? It'll run this forward pass in this neuron, or this class, sorry, not neuron, in which it'll return log likelihoods and set that to be equal to sample losses, and then it'll take the mean of all the sample losses. So it'll take the mean of this array with all the log values of the confidences in them. It'll mean those, and then it'll return it as data loss because that is our mean loss of the entire batch of inputs that we sent. So we're taking this array, we're taking the mean of it to get one value out. So we're going from multiple loss values for multiple batches of inputs to just one average loss for that entire batch, for the entire set of batches of inputs. Alright, so that's pretty much the code for calculating loss. I put like these arbitrary numbers in it, but they don't kind of work because we need like an actual set of data for this to kind of work. I can't just make up random numbers like this. So rather than just trying to create or pull a different data set to implement into this Scratch work, I'm just gonna go ahead and move us on to the framework part of this video, and we can see how loss is calculated in there, and look at the optimization and all like the code they use to kind of represent what we've been doing so far, but in a much more succinct kind of short way. And that's really useful if you're already knowledgeable in the subject and you know what you're doing, but it's not really good for people that want to understand fundamentally how these things work. So it's not really good to start learning from those frameworks. It's better to, conceptually understand the topic first before you start using the shortcuts. So why don't we go ahead and go into Google Colab actually and check this out. Alright, so welcome back. We're in Google Colab now, and the Google Colab is a free IDE, so you can just go ahead and look it up and create a collab right now, I guess, and code along with me, I guess. So in Colab, I imported the framework that we need. It's called TensorFlow, and we imported it as TF. TensorFlow is a machine learning framework in Python. It's very useful, simplifies the code a lot. As you can see, this is the entire network plus some actually. This right here is the beef right here. Is the beef where all the work goes down. This is the optimization part. We specify what optimizer you use. This is where you specify what loss you use, and this is where what you're classifying by. This is where you specify what you're classifying by. So we're classifying by accuracy in this model. But let's start from the top. So we've imported TensorFlow as Keras. So from TensorFlow, we're importing Keras, which is another framework, but it's more specific to neural networks and AI. We've also imported Matplotlib, which is a way for us to visualize the data, and we've also imported NumPy as if needed. So the data set we're going to be working with is a data set of handwritten digits, and these digits are represented as images of numbers, right? So these are handwritten numbers of like 7, 6, 3, or 2, and I'll show you an example from one of these I'll show you an example of one of these images. It looks like this. It's 28 pixels by 28 pixels long, and it's the number 7, right? So we can all visually see this is a 7. We're gonna have the computer train on this data so that it can tell that what any number is, based on what any image you send it of these digits, right? So if we send it a 6 in this format, the computer will be able to tell it's a 6. If we send it a 9, it'll be able to tell it's a 9. And to us, this is pretty easy, right? We can just look at it and be like, oh, it's a 7 because we recognize the 7. But for a computer to do this without using neural networks, it's insanely hard for them to do this without using any neural network. It was thought to be impossible, I'm pretty sure, before people actually started exploring the idea of using perceptrons and neural networks to solve these complex problems. So this is very hard to do without using neural networks. All right, so we're gonna import that data set right here and split it into a train set and an X train set, a Y train set, an X test set, and a Y test set. So we'll load the data set into it. We can go ahead and display the training data set right here. And the data comes out in a 2D array, I think. Yes, 2D arrays, in which these pixel values are a representation between 1 and 256 of how dark that digit is, or how dark that pixel is. And the 2D array is kind of like a map, like a grid board, in which you can kind of place pixels. So like all these data points are specific to pixels in the image. So why don't we go ahead and display this thing again? So these would kind of be the columns, and these would be the rows. And then the numbers you see here all represent pixels. All these numbers, all the zeros and the 0.67s, 0.85s, 0.992s, they all represent pixels. But the zeros represent pixels that are, in this case, all purple, I guess. And these numbers that are getting bigger and bigger, they represent pixels that get lighter. So in this case, there'd be like the more yellowish pixels. So the bigger this number gets, the more lighter it gets in this case. But for general purposes, we can think of it like this. The zeros mean the pixel is white, and the bigger the number gets, the darker the pixel gets. So this is how kind of like the color is determined in this image. It's based on these individual pixel values that all represent color between 1 and 256. And 1 would be like the lightest color, so white, and 0 would be the lightest, so it'd be white, and 256 would be black. But these are in percentages. So this is 0.992 of 256. This is 0.58 of 256. This is 0.980 of 256. So this is 98% as dark as it can get. This is 58% as dark as it could get. This is 89% as dark as it could get. So these numbers just represent color. And the indexes, or where these numbers belong in this big 2D array, is kind of what determines where on this image that pixel is colored. So this 2D array is kind of like taking the image and representing it like dot for dot, but using numbers instead of like pixels. So that's what this data kind of is, and it's always good to understand the data before you work with it, because the whole point of neural networks is to better develop connections and relationships between data. So if you don't understand the data, if you don't understand what you're doing with the data, if you don't understand what you want from the data, you're not going to be able to do anything with the data. So what we want to do is go ahead and flatten this training set, this 2D array, into a 1D array. And we can go ahead and do that by reshaping it to be the length of this training data set, which is basically the original data set divided by the number of pixels, 255, that's allowed. So it goes from this length, right? So from the length of the X trained data set, this, up to 28 times 28, and it's 28 times 28 because it's 28 pixels by 28 pixels. So you're compressing 28 rows by 28 rows into one entire row. So you need to have um, a representation for every single value that's possible. So which is like 700 something. 20 times 28. 784. So you have a total of 784 possible pixels in this image right here. So you have to when you're flattening the data set, which means you're creating a one-dimensional data set, you have to be able to include all of these points. So it goes from pretty much 0 to 784. Or goes from the length of the X-train data set to 784. And this is the same for the test data shape as well, because we have to do the same for the test one. If we're going to be training it in this method, we have to do the same for the test method. But we'll be using X-test instead. And we already showed what this looks like down here. So now we get to the model part. And you can already see how insanely simplified this is. Imagine you were trying to learn how a neural network works, and you just saw this. Keras.layers.dense 100, input shape equals 784, and activation equals ReLU. Like, what sense would you make out of that? Well, we can start making sense out of it because we know it's talking about layers. Dense refers to how many, well, dense refers to the layer, like, size, pretty much. And so we understand that it's giving it 100 neurons in the first layer, sequential layers. It's referring to sequential layers, so layer after layer. So then the first layer will have 100 neurons. And the shape of the inputs, how many inputs we're going to be sending into the first layer is 784, because it goes up to 784 pixels in this entire image, right? It's 28 by 28 pixels. It goes up to 784 pixels in the flattened out data set. So this is how many inputs we're going to be sending into that first neuron. And we're going to be using an activation function of a rectified linear. So we're going to be using a rectified linear unit activation function on the first layer. The second layer has 10 neurons, and this is going to be our output layer. And each of these neurons, 1 through 10, represents a number 1 through 10. So 1 is going to be 1, 2 is going to be 2, 3 is going to be 3, 4 is going to be 4. So we have 10 classes we can pretty much pull from. So if we give this model a number between 1 and 10, it should be able to predict what that number is, because it has 10 classes. And on the last on the output layer, we're going to be using the softmax function. We could also use the sigmoid function if we wanted to, but we'll stick to the softmax because that's what we've been working with. And then the model will actually, this part is the optimization part, so a composite optimization part. So it uses the Atom optimizer, which kind of works with the momentum. It has momentum into it, so we use Atom. I'm not trying to go into like the specifics, but we use Atom when we want to solve a repetitive task quickly. So this is like a pretty fast optimizer. That's why we like it. It's fast and efficient. We're going to be using the categorical cross entropy loss function, the sparse categorical cross entropy to determine our loss, and we're going to be doing it based on accuracy. And then we can actually start fitting the model with the training data sets. And so we fitted the X-train data sets and the Y-trains. So the Y-trains are pretty much our one-hot encoded vectors. So our Y-trains are pretty much our desired outputs. So these are how we're going to classify what we want. These are going to be our inputs that we send in to get out a predicted output. And epochs just refers to however many times you're going to be recycling the entire data set. So this just means we're going to go through the entire data set 5 times in this one fitting. So all this data, all this training data, right, in this that we called up here is going to be sent through this network 5 times on repeat. So if we go ahead and run this, it'll run through the first epoch, and it's deriving accuracy right here. So we got a 92% accuracy in determining what the image was in the first epoch. The second epoch, we got a 96% accuracy. The third epoch, we're getting a 97% accuracy. Or the fourth epoch, we're getting 97%, 97.9. And the fourth, we get 98% accuracy. So we can go ahead and see if we can. Why don't we go replace that with sigmoid and see what we get as well? Alright, we're getting better numbers for the first epoch. 92%. Oh, the second epoch's already at 96%. Third epoch's 97.3. Fourth, it's going much faster too, I think. Fourth epoch, not much faster, but faster. Fourth epoch's 97.9. And the fifth epoch is 98.3. So I think this the sigmoid function works a little bit better, but for our purposes, let's just stick to softmax for now. Alright, so this is pretty much it. I know we didn't explain conceptually kind of what how optimization and we did kind of explain conceptually how optimization works, but we didn't go into the specifics regarding math. And that's because it's calculus wasn't a part of the prerequisites for this this video course, so we can't really go into the specifics because we need calculus. So this is the next best thing we can do right now, and you can just see how ridiculously simplified this is, right? Like look at what we can just do with one line of code. We can initialize and optimize. We don't have to code any of this out. We can initialize the loss. Look at do you guys remember how much we had to code for the loss function? It was like 2 entire classes, so we can just call it like this and have our loss function ready. So it's insane what you guys can do with these frameworks. It makes coding so much more easier and efficient, but it's harder to learn from it, so there's always a downside. Yeah, so that's pretty much how you code a neural network from scratch in this framework, which includes backpropagation and optimization right here. So, yep. Alright, so I think that's almost, yeah, that is pretty much it for the video course, I think. So we went from scratch, not knowing anything about neural networks, to conceptually understanding how they work, to mathematically modeling them on individual neuron scales up to whole batches. Then we programmed that into object-oriented programming so that we can make the code dynamic. We programmed an entire forward pass, at least in object-oriented programming. We calculated the loss using classes and object-oriented programming, and finally we took a look at external frameworks that we can use in order to actually create these networks with backpropagation and optimization included into its function. So this is probably the end, yeah. All right, so it was a pleasure going through all this stuff with you guys. Hopefully, hopefully you guys fundamentally kind of understand how some of the forward pass math works, and at least how neural networks conceptually work, up to optimization and backpropagation, and hopefully you have a solid understanding of how that works, because that's what I wanted you guys to get from this course. And now after this kind of demonstration, hopefully you guys understand, or kind of, not, you don't have to understand, but hopefully you guys can like process through how a framework and programmed neural network kind of looks, and how we split data into train and test data sets, and we kind of work with that. What epochs are, some of the new stuff. So yeah. All right. So hey, I'm editing the last video for the video course right now, and I just wanted to let you guys know that I am thankful for whoever stuck through the entire video course, spent a couple hours of their day, and listened to me ramble on and talk about something that I am excited about, but I'm not sure if everybody else is. These videos ended up being way longer than I had ever planned them to be. And I couldn't even actually get everything I wanted into these videos because some of the concepts got way too difficult for me to explain way too fast. And hopefully if you guys stuck through, you gained something from here. Hopefully I didn't leave you more confused than you already were. yeah, so you guys probably know more about neural networks hopefully now, like about how they work, what you need to make a neural network, what's like the parts of it, uh, kind of how to mathematically model them, how to program them into existence from scratch using object-oriented programming, how you can even program them in Keras, and you know, all sorts of things that we've been learning. So once again, I want to thank you guys for watching the video course. It means a lot to me, and yeah, just also want to remind you guys to fill out the Google form. The Google Forms, there should be two, one before and one after. Uh, but one before watching and one after watching. I just want to remind you guys to fill those out if you can. It'd be very nice. They should be pretty short, and I really appreciate the feedback. All right. Have a great day, guys.